Hey, everybody. Thanks for having me, and I'm excited to talk to you about vectors. I have been doing this for the last couple of years. Some of you might have seen me doing this on LinkedIn for a while. And yeah, the first question to kick us off, I would like to get some idea of, have you used vector search before? Have you just heard about it or used it or actually build a system around vector search? I would love to get some responses in chat with people's different experiences. And then, that also helps me calibrate my explanations. So as you kind of gear up to actually kick off, if you can share your expertise level, it would be helpful. Alexandra or Francesco, to get us started. All right, so we have the first person using Spacy. So that's a Python library for turning text into vectors, right? It's an NLP library, and then Elasticsearch as a vector search solution. So Elasticsearch now also supports vectors like many other databases do. I see another version of Elastic. I see Quadrant, which is a vector database. And then there is also a mix of folks who heard about it but haven't used it. Cool. All right. So we have quite a big range of expertise, which is always great, and ideally for the newcomers into the field, this like your first step. But then I'll try to also share some resources for where to go next, where to dive deeper into the topic. But hopefully I can, at least get you a little bit excited about what this is all about. All right. I think we have 3 minutes in, so I think let's just get started. And this is also being recorded, so for the folks who join later, I think there is a way to watch the beginning as well. All right, so hey everybody, I'm Daniel. I'm, as introduced, I'm one of the co-founders of Superlinked, and we are building this system that helps turn all kinds of data, not just text and images, into vectors. And today I'll talk you through kind of some of the basics of what these vectors enable us to do and how they enable us to understand our data. We'll talk about a little bit of the math, but I'll try to make it as painless as possible and as kind of picture-driven as we can. And then we'll, look at some practical examples, and eventually basically talk about how to build the system around it. We'll make some system design diagram together and go from there. I am sharing my screen.
Daniel, I think I mean your screen is visible, but I think if you can try sharing it once more, maybe for the audience members who are joining in right now.
I see. So the people who join later don't see the screen, or how does this work? Okay, let's see.
Guys, if you could just comment down below and let us know if you, Bill, I see your comments.
It is. Yeah, it is.
Okay, perfect. It's visible. Great.
All right. Yeah, we have been doing this since 2020, and still the basics of video calls, sometimes escape us. Okay, so let's dive into this. So I was thinking about a good way to kind of motivate this whole idea of turning data into vectors, and if I dive straight into the math, everybody will just quit the call. So I'm not going to do that. We are going to look at some pretty pictures to start with. There is this, and I hope that the screen share survives me switching to another tab. So this is a tool called Atlas by nomic.ai. And what this is basically a data set of tweets. And they have been turned into vectors, right? And that process, takes a tweet and makes a 2D coordinate from the tweet, organizing the data set, organizing the tweets in a way that semantically related, tweets talking about the similar thing are projected to a similar set of coordinates, right? And this is like a little bit dangerous because this is like an actual tweet data set, so there is all kinds of stuff in there. But I thought that this is a way to understand what this data structure allows us to do. So here we have, a bunch of tweets. I think it's like maybe a couple million tweets. And there are some clusters in there, right? So for example, this should be pretty safe if we dive into the animals. Then you see that the dogs and cats and stuff are clustered together, and then we have birds, and then let's see if we can do something. Okay, so this is like sufficiently dog-like. On the left, they actually render in this tool the actual tweets. And so you see, we have started with something quite complicated, a million tweets. And we have managed to have a single view where somehow we organized everything by the topic, and we can dive in and out of this and actually understand what's going on in this unstructured data set, right? So this is the super powerful aspect of turning your data into vectors, is that it allows you to build these kind of maps. And in this example, it has been done to textual data, but you can do this, in principle, you can do this with anything, right? You can do this with your users, your customers, your products that you are selling. Any data set that you have, you can vectorize and start to understand, okay, which users are behaving similarly to each other, which products sell at the same time, or have a picture that looks similar, or have a description that talks about the same things, right? So it's a way to make a map, basically, map of your data. Okay, so that should be quite exciting, and you should already have use cases popping into your mind of building a recommender system or a search system. Nowadays we have this very modern retrieval augmented generation pattern where we are building search systems that then help a language model answer a question. This is super useful for analytics, right? The user clustering example I mentioned. So this is where all that hype around vectors is coming from, right? People see it as a super transformative technology because you can build all these things on top of that basic data structure. Okay, so turning data into vectors, a good idea, useful idea. Let's look at kind of how it's done, basically, right? Cool. Now we need to first of all understand what a vector is, basically. And so I have prepared just a quick visualization of a couple of things. So in basic terms, vector is literally just a set of coordinates in some kind of space, right? If we want to visualize these vectors, then it's useful to start with just a two-dimensional set of vectors. So we have two vectors A and B, and these are their coordinates, and then you can, plot them like this. This is pretty simple. Now, and I'll not go through the plotting code, but we will share the notebook afterwards, right? So you'll be able to go through this also by yourself. But basically, okay, so we have two vectors. They can represent anything, but they're also like pretty simple. So that's how that looks. Now, what can we do with vectors? We can add them together. Just if you use NumPy, which is kind of the main math library in or the main kind of linear algebra library in Python, then this is very simple. You can just add them this way, and the intuition of vector addition looks like this. So we are literally just adding up the coordinates, right? We're summing up the first dimension with the first dimension, second with second, and by adding the red and blue vector, we get the green one here. So in that same way, so you have to think about the green vector, like what is that, right? If our red and blue vectors were products we are selling in our e-commerce store, and we add one product to the other product, like what's the intuition there, right? One way to think about that is basically that you have taken these two representations of your products, and you have taken kind of a union of that representation, right? So you have some new vector that represents both of those products at the same time, right? Now, why is this useful? Well, you can think about applications where, let's say you want to represent the preferences of your user in your e-commerce store, and you have a history of what products this user bought. One way to represent, build the user vector is you can just literally add up all the product vectors that the user purchased, right? And then that user vector will somehow aggregate all the knowledge of what this user is about. So addition, think about it as kind of a combination of the information that the vectors encode. And then the next useful operation, especially when we build search systems, where a search is basically just a way to calculate distance between these vectors, because you can have your search query, turn it into a vector, and then go into your index and find the nearest neighbors, right? And this is what all the vector databases that you hear about do. But what's the intuition behind, like, what do we mean by nearest neighbor, right? Typically, it's either a dot product or a cosine similarity. Basically, you want some operation that takes two vectors and returns a number, right? Because then it makes sense to order by that number. Okay, so let's look at, and this is like typically people kind of gloss over this part, but we just, but I think it's useful to actually understand how this behaves, right? So for dot product, this is just the basic. Okay, you calculate some kind of score that is for the input it takes the two vectors, and for the output you get the scalar. So for our two red and blue vectors, you get 5, which is kind of like, okay, is that a lot? Is that not a lot? What does that mean? And to unpack that, I think it's useful to look at how that value changes as a function of those vectors changing. And I thought about ways to kind of visualize that. And basically, here is what I came up with. I hope you can see this. So at the top here, I have basically the red vector that we had is fixed, is the same. And then I rotate the blue vector around the origin of the coordinate system, right? So this is the unrotated one. This is the basic case we started with. Here it's aligned with the red vector. Here it's rotating left. Here it's completely opposite, and eventually rotated further. And as we do the rotation, starting with the full alignment and proceeding to the right, the dot product does this, right? So it goes from, I think this is 7-ish, let's say, based on the chart. And that's for when the vectors are aligned completely, right? So it's the maximum value of dot product when the vectors are completely aligned. And the minimum value is basically 135, which is when they are completely opposite, right? So because now that gives you context for that 5 we had here, right? So 5 is pretty high, but not, basically that's the 0 here, right? It can get higher if you do the full alignment. So this is how, all the similarity search indices in vector databases, this is the metric that they use under the hood. Either this or cosine similarity, which I'll jump to next. I see that folks are interested in the notebook. I'll just drop that in the. Wait, anyone with the link? Okay, let's move it over for now. Okay. Hopefully you can open that. So this is the intuition behind vector similarity. The dot product version of that changes like this as the vectors are aligned or opposite to each other. And then, cosine similarity is literally the same thing, but you divide it by the product of the length of the vectors, right? And what that does is it just scales it to the range of 1 to -1, the values that you can get, right? So in principle it's the same, it's just independent of the vector length, right? And so that's what's going on under the hood in all of kind of searching type use cases for vectors. Any question? Feel free to ask. I would like to make this as interactive as possible. If there is anything unclear whatsoever. Okay, so question, is the dot product cheaper to calculate versus cosine similarity? Well, I think the answer is yes. In general, there might be some special cases, special optimizations where that's not the case, but just in principle, since cosine similarity is basically dot product with the extra division, I imagine that the dot product has to be cheaper. Yeah, Rohan, to your question, I'll basically show building how it looks to build like a super simple vector search system. And that's where we will use the dot product to score the difference between the embedding of the search query versus our index. All right, cool. So we have seen that somehow it's possible to turn all tweets, for example, into vectors. We have understood what the vector is, just the coordinate point. And we have looked at a few different operations that you can run on these things. Now, let's fold this up. All right. So the next step is actually doing something useful. And that process starts with actually figuring out how to turn data into vectors, right? Because we have just previously we have just said, okay, my vector is the coordinate 2, 3, right? But to do anything useful with this, we need to vectorize the data, right? And one way to do that is this very useful Python package called sentence transformers that hosts a number of open source models that have been pre-trained and can be run on your data and specifically on your textual data to turn it into embeddings. So just install that. And here is kind of the simplest possible example, right? So we just use the sentence transformer library. We choose a model. Okay, this is not used. we choose a model, and then basically we have some textual data, right? In this case, we have a couple animals and couple transportation means of transport, and then we literally just ran the model on the data to get the vectors out. Now, if you do that, you'll find out that it depends on which model you use. That dictates the size of the vectors that you'll get out. And in the case of this model, we get 7 vectors because there are 7 items, and each vector has 384 dimensions. Now, I want to make a quick detour here and look at this thing. And I'll also drop a link to it into the notebook. But basically, this is a leaderboard on Hugging Face that's constantly being updated, which shows basically performance of different embedding models on different tasks and data sets and benchmarks, right? So there's a very long list of all kinds of different models. The interesting thing to look at is model size, because that will dictate how difficult it is to run that model, how much compute you need, how much time you need to run it. So you want, the one we'll use as example is kind of like near rank 56 around here, and it has something like 100 megabytes in terms of the whole model. And then different model produces different number of dimensions, and it can consume different number of tokens on the input, right? So you can give it even a whole paragraph or even a whole document for some of the models, and they can take that whole thing and turn it into vectors. For models that have small limit of the size of the input, you will have to kind of split the input up, vectorize sentence by sentence, and then we talked about how addition is basically a way to combine the vectors. You'll have to add up the representations, the vectors for each sentence, and then once you start doing that, you realize that okay, maybe I shouldn't just add things up. Maybe I should normalize it because my numbers are getting very big. So we take kind of an average of the vectors, not just the sum. Okay. So just that's kind of a first step towards figuring out, okay, which model do I want to use? But for the purpose of our session here, we just go with something very small. This has 100 megabytes, and it performs within 20% of the state of the art. So yes, you can improve by using one of those models at the top of the chart, but this is something that we can start with. Okay. All right, thanks for sharing the notebook link. Okay, so basically we have these 7 things. We turned it into vectors. Now we want to understand how that actually looks inside, right? This thing is basically each vector has 384 floating point dimensions. So printing that out doesn't help. Actually, let's see if this thing works. Okay, right. So you will not get very far trying to read this data structure, and so in order to make that map out of it, right, we need to reduce the number of dimensions, right? We need to somehow go from 384 to 2, right? Because our chart has 2 dimensions. Obviously there are very many different ways to do that. One of the simplest ones is called the principal component analysis, PCA, and yeah, it's just 2 simple function calls that you can perform on top of our vectors. So Lauren, 384 is the number of if we had a representation that would be more like a sparse vector, so it would be for each word in our data set, it would just record, does the word appear in that input or not? Then you would be right? We would have one word per dimension. However, that's what we call sparse vectors, right? And what we see here in this exercise, this is what we call dense vectors. And it's dense vectors because, as you can see, all the values basically are non-zero, right? And you can't really tell. So, first dimension here, you can't really tell what that actually means, right? Like what does it mean that this document has minus 0.12 value on the first dimension of the vector? It doesn't correspond to any one particular word. Think about it as just the model trying to encode what is the point of that chunk of text. And we give it 384 numbers to produce this encoding, but we don't really dig, or we can, but normally we don't really dig and start asking like, okay, but what does the first number mean? What does the second number mean? But yeah, you are thinking about it right. Like what, because in the kind of alternative technique, indeed, each of these numbers would correspond to a word in the underlying corpus. Okay, so now we are trying to make a chart, right? So we are trying to reduce these dimensions to 2. We use PCA, and like we don't have to go into the detail of how that works, but somehow it tries to preserve the structure while projecting it to a lower dimensional space. Preserve as much of it as possible. Of course, that projection is lossy, right? We are kind of turning 384 numbers into 2 numbers, and so we will lose a lot of the information. But our hope is that we preserve enough of it. And actually, here we'll be able to check. Did we manage to preserve something? Because we'll make a plot, and we'll see if the dog and cat are close by, and if the dog and sheep are further apart. Right? That will be the way we judge if this thing actually works, right? Okay, so we make that plot and we get, okay, this doesn't fit. And we get this, right? Okay, so what's going on here? We have the 2 dimensions that we reduce the vectors into, and then we have our 7 input strings, and they have been laid out in the following way, which actually makes sense, right? We have the means of transport grouped together here. We have the cat and the dog, which are, let's say, animals up here. And then we have kind of other types of animals, horse-like animals down here. So this kind of makes sense. Now, if somebody can volunteer some ideas for what I should add here, and then we'll see where it lands. I think that could be an interesting exercise. Any suggestions? All right, bicycle. So bicycle is a means of transport, right? We would kind of hope that this gets projected near those other things. Okay, we have one more animal, and then let's do one more kind of none of those things. Apple is great. Okay. Okay. Something totally dissimilar. VP, I think eigenvector would do the trick. So I have to appreciate the comedic value there and add it. Okay, cool. So we have added one more means of transport, one more animal, a fruit, and mathematical construct, let's say. Now, live coding is always fun, so let's hold our breath here. Okay, so we have 11 things in our vectors. Let's redo the plot. All right, what's going on here? Okay, so bicycle got with the means of transport. That's good. Ferret is here, and somehow it's closer to cat and a dog than horse and a pony, which, you know, let's say it's a small and big animal clusters, so that makes sense. And then we have apple here and eigenvector here, which, you know, like it's the other, maybe this is the other cluster. I want to try one more thing, which is just to show you that actually these don't have to be single words, right? So the model that we have chosen, I think, you know, has at least like 100 token input or something. So we can have a whole sentence here. So for example, you know, I like, so maybe we don't do it to this one, but we do it to a ship. This is the fastest ship in the world. Okay, so this is kind of a pretty big stress test, right? Because I have now surrounded the ship word with a whole bunch of other stuff, right? And then, okay, well, let's switch this for Mac and see if that gets close to Apple. Okay, so but let's see. Okay, I think it's important to understand that you can have any string here as long as it fits into the maximum token size for the model. All right, let's rerun this. Oh wow! All right, Apple and Mac are basically very close, so that's good to see. The ship is kind of traveling outside of the means of transport cluster, but it's still kind of in that region, right? It didn't go all the way to Ferret or to Mac. So you see that this thing is actually kind of robust, right? And then, you know, when you play with the notebook yourself, you can start to do things like a ship full of apples and then kind of see what happens. Rohan, Mac and Apple is close because Apple makes Macs, right? Apple the company, of course, not the fruit. And then, yeah, maybe one more thing to realize is that this is very unstable, right? Basically, if we change any of the input, this thing can completely shuffle itself, right? There is no statefulness between the edits, but we would still hope that the clusters will kind of roughly represent the data, right? So if you are trying to build a system on top of this, and obviously you need to update it over time, you have to be very careful about those types of assumptions, right? I have made a thing that works and I'm changing it or adding data. Does it still work, right? This is different from building software where you can have a unit test and it's done, right? And then you know that it works. This takes you closer to data science, machine learning, where you need sort of probabilistic ways to evaluate, okay, do I still have these things that I expect to be close? Are they still roughly close? These opposite things, are they still roughly opposite? And so on. Okay, cool. I see we have a fun conversation happening around flavors of apple, so that's good. I read that every vector encoding model includes a stochastic element, so you can't even assume the same vector for the same word and phrase. It depends what you feed into the model. If you feed kind of a random vector together with your input, sometimes that can improve some of its properties, but then of course the output is unstable, right? But that is not necessarily always the case, right? You can also make it so that the same model with the same version will produce the same output for the same input. That also is possible. Okay. Let's go a bit further, and let's look at some actual like real data here, because you know we have been looking at some toy strings so far. And here we are looking at the data set of movies. So we have and this is from our friends at Netflix. Basically, we have, and I have done some little bit of data prep, but basically, we have imagine a table with a bunch of movies where we have descriptions for those movies. We have genres, which is a list of kind of genre names. Then we have titles, and we have release year, and then that's just the timestamp out of which we made the release year and an ID. So that's our data. For the purpose of running this quickly, we take a subset of the movies, so just movies released in 2022. And what we'll do is we will take the descriptions, right, and turn those into vectors. And we'll add a new column for this in the data frame. Same as we did before, right? Okay, so we do that, and we have a new column here, and we see that coordinates made it in there. And we, I think we have about 300 of these vectors movies after we did the filter. So this runs super fast. Actually, hopefully I don't break this whole thing by just rerunning this to show you how fast this runs, just to give you an idea. Cool, so that was it. And that's, in a default collaboratory kernel, right? I'm not using any separate service to host the model or anything like that. I'm running everything in memory in the notebook, basically. And this is about 300 or so movies. I think we can. Is it shape? Okay, 369 movies. So it's reasonable. And the next thing is, okay, let's make that map again, right? So what I do is I take first 20 movies from that filtered set. I take out the vectors from the data frame. I combine the movie titles and the genres to label the points in our map. And then I do the projection to 2D, and I get this. So remember, we are only using the descriptions for the vectors, right? We are not actually vectorizing the genre information, right? So in a way, but we are plotting, we are showing here the genre information, right? So we can check here if we are inferring roughly the correct genres from the descriptions by seeing which kind of genres will get clustered together, right? So for example here, and these are a bunch of not very known movies necessarily, but for example here we have a thriller movie and another thriller movie projected nearby, and we are only getting that out of vectorizing the movie description, right? So the model doesn't know this kind of summarizing information that actually is both are thriller. And so that has to be inferred from the description, and it seems to more or less work. And of course, some of these descriptions are incomplete or not so descriptive, and that's where the real work starts, right? Like, okay, how do we make this work better? But roughly, there's like a little comedy, so comedy, little comedy cluster here, and so on. Any questions? So Ariel has a question. Rules of thumb on when to use PCA. In general, I would say that use PCA only for visualization. Don't actually use it in a production system, because it will reduce the number of information a lot. And the way you can get the intuition for this is you basically, by assuming that you can run a PCA on the vector and still get quite a good representation out, even with lower dimensions. Basically, what you are saying there is that the model is inefficient, that it doesn't fully use all the dimensions, and so you can compress it. But that's actually not true, right? The models are trained to be very efficient, and so if you reduce most of the dimensions, you'll lose most of the information, right? It's kind of like just grabbing the first two dimensions of the whole vector, right? It's almost that bad, because the dimensions are decorrelated from each other because they encode the maximum number of information. So that's a little bit the intuition here, right? Now, if you want to have smaller vectors, because you have very many of them and the vector database is getting expensive, for example, OpenAI now released this embedding model, which they call the Matryoshka model, which is basically you can grab the first set of dimensions from the longer vector, and they are optimized to encode as much of the information as possible. So the model is optimized to do that. And in that case, it sort of makes sense, right? So you can look into that if you want very small vectors, or basically on the benchmark that I have shown you, look for the column with the number of dimensions and pick something that has few. And 380 dimensions is pretty low, so that you shouldn't have a big problem hosting that. Okay. Let's keep going, and then I can also check out some of the questions. So okay, so this kind of works, but also kind of doesn't, right? Like we have a drama next to comedy movie, and it's imperfect. So another thing we can do is actually vectorize the genres, right? And plot that, right? And what we should see from this exercise is better clustering, because we are using the same information to do the vectors and then do the labeling when we plot, right? So that's kind of one-to-one. And so if we do that, then we get something like this, right? So we have a comedy cluster here. We have a documentation, which I think is documentary cluster here, and then a bunch of horror movies, right? So this puts the genre clusters together in a more precise way. But the descriptions could have extra information which now we are not using at all, right? So that's just a way to get a sense for how this thing works, right? Okay. We have, is there a way to show those data points as clusters rather than manually checking? You can run a clustering algorithm on top of the vectors, and then identify, let's say, k-means, right? Identify the clusters and, let's say, plot the center points of all the vectors that belong to each cluster. And then you can calculate how far those clusters are apart. So you can do a lot of analysis with clustering on top of this, right? That's also how these guys kind of have these labels, right? Animals. They have done some clustering. They have figured out kind of a commonality between those points and then generated the label, right? So you can definitely do that. Okay, let's have a look at what it takes to build a search system, because that's the name of the talk. Okay, so basically, as I said, in the search scenario, right, we have a search query, and we need to turn the query into the vector and then do the similarity search, right? That's kind of how this works. So I have a simple method where we get the query, and we have turned the genres and the descriptions into vectors. So we have the data frame, and then we have the parameter that says which of the embeddings we want to use and how many items we want to retrieve. And basically what we do is we encode the query. So we turn the query into a vector, and then we calculate the cosine similarity, and we order by this and drop, and basically just reduce those results to the top n with the head. Okay, and here's what we get, right? So if we search for educational documentaries, we get a bunch of, and we are searching the genres, right? We get dramas out. Let's try to run this thing and play with some queries. So let's just try something simple just to see if this works. Okay, so horror gives us a bunch of horror movies. That's good. What about the scary? Kind of a mix, but still getting a lot of horror in there. Now, I'm using the genre embedding column, right? So what I can do is also use the description embedding, right? So here I'm looking for embeddings that are close to the embedding of scary, right, in the description, or among the vectors that represent the descriptions. So what does that do? Now the genres get kind of somewhat unfocused, but the descriptions should sound scary, like violent con artists, stone cold killers. Okay, so that works. Monstrous creatures works, and so on. Some zombies and so on. So this kind of works. Now we can try happy, see what happens. Okay, there is literally a happy, like a keyword match, laughter, romantic, right? So happy things, and so on, right? Again, you'll have the notebook, you can play with this, get a feel for how this works. Now, as the next step, right? This is like building a search system. Okay, you don't want your users to switch between which embedding of which part of the, right? We're like building a search box for our website that has movies in it. We have to make this somehow much nicer, right? And so that's where this kind of messy work starts, right? So for example, you say, okay, let's not choose, let's actually combine the genre string and the description string. Let's encode the combined string, and then we have these compound embeddings in the table, and we'll use that for searching, right? Because then we don't have to choose where the vector is coming from. We are using all the data, or at least, those two columns, genre and description, at the same time, right? And then, okay, educational documentaries then gives us something with like documentary sounding things in the genre. And then, we have interviews and documentary type movies appearing without having to switch between the sources of the vector. So that's kind of an interesting trick. And then, the way this kind of goes from here is you say things like generate a vector useful for searching with searching of movies of the following movie, right? This is called prompt engineering, right? You are basically trying to cobble together a string that describes your data, and you are prefacing it with some kind of intention, right? And this actually helps. So you can do that. And by helps, I mean the relevance of the results improves. Because there is a difference between finding a document that's similar to the query embedding versus finding a document that would be a good response for a given query is not necessarily similar, right? It's like slightly different relationship. And like you can play with this and see what it means to actually improve the results. And that's that kind of kicks off the whole process of tuning such a system. And it's a very long path, right? Now I'll close with a couple of things. I wanted to show you a slightly better way to figure out how to turn complex data like this into vectors, because there is release year. Like, what if the user is looking for kind of recent movies that also match the query and so on? We at Superlinked, we are building a system that makes it easier to turn complicated data into vectors. So I will just give you like a sneak peek of that. We haven't actually properly launched. We are in a private alpha with the product. So here is just a super quick sneak peek at the product. And feel free to message me afterwards, and I can give you an invite to the product, because this is private. So just a quick summary. In our SDK, you define, okay, here is the schema of my movie, and we have a thing called spaces, which are abstractions over embedding models. And right now we have text type models, and we have something we call recency space. So this allows you to turn a timestamp or a release date of a movie into a vector. And we have things for ways to encode numbers and popularity counters and all kinds of other complicated data. We will be adding image embeddings, which is useful for recommender systems, and all kinds of other data types later. But the main point is you define these spaces, you build indices out of spaces. When you define the spaces, you bind them to different parts of the input. And then you can do queries that kind of look like this, where you run a query against the different spaces the same. For example, in this example, we ran a query against the title and genre and description embedding at the same time. But what we can do is we can tune the weight with which those different embeddings factor into the result. And on top of that, you can also bias those results to recent movies or older movies, and kind of navigate the trade-off with the simple query language. So that's just a quick sort of sneak peek at our product, but I don't want to make this too salesy. You can definitely get started this way and iterate and play with building a system yourself. And lastly, I wanted to show you a quick system diagram of how a vector-powered system looks like, what kind of components you need, and then give you these two resource links. Let me just move this box out of the way. Okay, I prepared this because I had a suspicion we'll be running out of time. So when you build a vector-powered system, I hope you can all see this, by the way. You'll be thinking in this kind of setup, right? You'll have your data where, in the example, we just loaded it into a data frame, but you probably have some kind of a database. You might have a data warehouse with your behavioral data that you want to vectorize to build user vectors, right? You have some data landscape on the left. The component that comes after that is you have to load all of the relevant data about your entities, and you have to turn it into vectors and somehow figure out how to turn different parts of this data into vectors and combine the vectors, go through the whole process, right? ideally you want to do as little of prompt engineering as possible, because that's where this randomness and kind of weirdness is introduced, right? So ideally you want to have some kind of schema-based setup, like the one I have showed you with superlinked. And eventually those vectors need to make it into a vector index, which is provided by the traditional databases. You have PG vector in Postgres, you have a vector index in Mongo, but also there is a whole bunch of very super interesting solutions that are specially built for vectors, and those are called vector databases. So you have to choose which one of those to use, and then on top of it, you want to build, you want to give your application a way to do queries, right? So you want to put some kind of service on top of that will help you get the query in, turn it into vectors, do the vector search, and then return the results, right? So this is the basic anatomy. Of course, all of these steps can get very, very complicated. Maybe you want to do re-ranking in your kind of serving layer here. Maybe you want to do real-time updates in your vector compute here, right? So that depends on your use case. Are you building a real-time personalized recommender engine, or are you personalizing emails that go out every night, right? That's the trade-off. All right, and in this process, one of your problems is choosing the vector database, and I have a resource for you for that. We have the basically largest crowdsourced table or database of vector databases, or different databases that offer vector indexing functionality. So this is at vdbs.superlink.com, and all of this data is basically, we collaborate on this with the vendors themselves, but then when a vendor wants to say, okay, we support, somebody wants to say they support a given feature, we ask for some kind of proof. And usually that proof is a link to documentation at least, right? So for example, okay, filters, ClickHouse, let's say, offers filters. I can go and I should be able to check. Okay, so this is a pretty general link, but ideally, those links are quite specific to that given functionality. And the quality of the data is a function of us working with the vendors, and all of the data is managed in a GitHub repository. So you can literally go here and see the pull requests of the various vendors contributing to the underlying data. This is each vendor has a JSON file and so on. I want to thank the Vector Hub community that helps us, or that basically maintains and extends the data there. And then the last resource I'll mention is Vector Hub, and that's for everybody who wants to dive into this topic deeper, learn more about vectors. Go to hub.superlink.com, and we have a bunch of super practical articles. We try to make it like a little bit more advanced, right? So we have a number of articles about the combination of graph embeddings with semantic embeddings. And then we have building blocks that kind of walk you through everything you need to build these types of systems. All right, I think we are just on time. Thanks everybody for your attention.